Good afternoon. My name is Atli, and for the past 2 months I've been managing research projects at Matorka. Matorka is an innovative food production company that has based a considerable part of its production on the use of geothermal water. Now I'm going to give you a short introduction of our project, Green Geothermal Growth, and hopefully we'll be able to have some discussions afterwards. The aim of the project was to implement profitable, sustainable, land-based warm water aquaculture in Iceland, utilizing local resources. The main objectives were to find opportunities to utilize geothermal water and wastewater from geothermal power plants to establish a whole new industry in warm water aquaculture, forming new species for mass production and export. The 3 work packages of the project were development and design of polyculture utilizing geothermal water, integration of aquaponics, and production of mycoprotein. I will discuss these work packages in greater detail as we proceed through this presentation. Why did we start this project? There were and are many good reasons for that. Due to the increasing number of people in the world, food production needs to be doubled in the next few decades. One way to increase food production is polyculture of plants, algae, and animals, where waste is minimized and water conserved. As fresh food is 70 to 90% water, water shortage has a strong effect on food production in the world. By implementing recirculating aquaculture systems, polyculture and aquaponics, we are contributing to the development of production systems that conserve water. Fishing of wild stocks will not increase in the foreseeable future, and aquaculture is therefore the only way to increase the availability of fish on the market. Food production in the world is largely dependent on fossil fuels. In this project, we focused on developing food production systems that are to a large extent independent of fossil fuels. In Iceland, we have unique conditions for food production due to the ample availability of both fresh and geothermal water and cheap electricity. Finding ways to use sustainable sources of geothermal water to increase production on aquaculture farms is an important goal. By 2030, the world food production must increase by 50% to meet our needs. One economically feasible way to increase food production is to recycle organic waste materials. This is one of the focus areas of the Green Geothermal Growth project. In 2025, global water demand will be expected to be up to 40% greater than water supplies. Iceland is in a unique position for food production due to the vast resource of clean, fresh water. Fishing of wild stock is not expected to increase in the next few decades. On the other hand, production of fish on aquaculture farms is expected to increase substantially. Aquaculture is considered to be the only way to increase fish supplies in the long term. There is a strong connection between the price of food and crude oil price. This emphasizes the importance of food production that's independent on fossil fuels and uses renewable sources of energy, such as geothermal water. Again, Iceland is in a unique position to use renewable energy sources for food production. And at Matorka, we are working towards a production system that's independent of fossil fuels. Polyculture refers to agriculture where many species of crops are grown in the same space. The term polyculture can also be applied to polyaquaculture, the farming of one or more species of fish in the same system. At Matorka, we are currently farming 2 types of fish, Arctic char and Nile tilapia, which we have marketed as Nordic tilapia. Matnorka's polyculture is still on a relatively small scale. We are currently farming tilapia in effluent from Arctic char. Polyculture on an industrial scale is being developed, and we have been considering adding more species to the system, such as new species of warm water fish and shrimps. Polyculture optimizes the utilization of resources, such as feed, geothermal water, and fresh water. Iceland has a great advantage over its competitors due to large resources of both geothermal and fresh water. Geothermal water plays an important role in polyculture. It enables good control over water temperature to maximize growth of warm water species, such as tilapia. Tilapia lives at optimum temperatures of 28 to 30 degrees Celsius and can easily be farmed in polycultural systems by adding warm geothermal water. Polyculture can be further integrated into sustainable systems, including aquaponics, alga culture, and fungi production. Warm water aquaculture is very important with regard to future food production due to the fast growth of warm water species. Warm water species such as tilapia are growing to market size within 7 to 9 months compared to 18 to 24 months for Arctic char. Aquaponics is a food production system that combines conventional aquaculture with hydroponics, which is a practice of growing plants in water without soil. Utilization of nutrient-rich effluents from aquaculture is ideal for hydroponics, minimizing the need for fertilizer and cleaning the effluent in the process. Once the water has been cleaned by the plants, it can be recirculated to the fish. This is similar to a natural cycle and minimizes the environmental impact of fish farms. The bottleneck for the production capacity of land-based aquaculture is most often the environmental impact of the effluent water. Aquaponics, if it turns out to be economically viable, could therefore become a breakthrough for land-based aquaculture stations and also provides opportunities for more local food production. That means less transport, increased food security, and in summary, increased sustainability. There are 3 main aquaponics production methods: a nutrient film technique, grow beds, and floating rafts. Based on the results from this project, a pilot aquaponics station has been designed and built in Fellsmúli, South Iceland. We did several experiments using the nutrient film technique to cultivate lettuce, basil, and mint in effluent water from tilapia. We had a system based on 70% recirculation of water, and the effluent was successfully used for hydroponics. In the nutrient film technique, a thin layer of water is flowing in plastic pipes, approximately 10 to 15 centimeters in diameter. The plants are grown in pots that are placed in holes made in the plastic pipes so that they can reach the water and the nutrients. This system is suitable for salad, herbs, and other small plants. Using effluent from aquaculture for the cultivation of vegetables and herbs is not the only option. Nutrient-rich effluent can also be used for alga culture, the production of microalgae for protein and/or oil. We did some basic experiments with alga culture in our pilot station using the species Nanochloris oculata, and we are currently focusing on implementing alga culture into our production system rather than hydroponics. Alga culture can be an economically viable option, especially in the effluent from warm water aquaculture. When it comes to alga culture, the use of geothermal water plays an important role. And the cultivation of algae is likely to be more cost-effective than hydroponics. Microalgae can be used to produce protein and omega-3 fatty acids, which can be used for fish feed or human supplements. Microalgae can contain up to 30% oil, depending on species and conditions. The rest is protein-rich raw material that can be used for feed easily. Microalgae are either grown in open ponds or closed bioreactors. Matorka also aims to treat effluent water to reduce nutrient levels. And for that purpose, alga culture is as good an option, if not better, than hydroponics. The cost of this effluent treatment would be offset by the sale of omega-3 fatty acids or by providing raw material for feed. Alga culture is considered to be an economically viable addition to aquaculture, especially where the effluent is warm. In Matorka's pilot unit and on our planned industrial-scale aquaculture farm, nutrient-rich warm water will flow from the tilapia tanks into closed bioreactors, where algae cultivation will take place. The system will be similar to the one on the diagram, except at this stage we won't be focusing on hydroponics or recirculation of water. The market for omega-3 fatty acids has been increasing, and the rise in demand is expected to continue in the future. This makes the production of omega-3 from algae an especially feasible option. The global market of omega-3 fatty acids is about 1 million tons. A total of 80% of the global omega-3 production is for fish feed, but consumer market is increasing by 15% per year. There is growing public awareness of some serious environmental issues concerning fish farming. The use of wild fish as an ingredient in fish feeds is a big problem, and Matorka is already experimenting with alternate feed sources, such as algae. Matorka is currently focusing on production of algae as raw material for feed production, as well as farming of soldier fly larvae using cuttings from fish processing. Some species of fungi are potential candidates for feed production due to their ability to convert organic waste into high-quality protein. We have been studying a particular species of fungus, Fusarium venenatum, which is very rich in protein. Test production of this species of fungus and feed experiments have given interesting results, and we'll continue looking into possibilities of using it as feed. This species is used commercially to produce high-quality protein for human consumption, popular among vegetarians. If its production turns out to be economically viable, it could also be used as fish feed. Mycoprotein production was commercialized in the UK in 1985 under the brand name Quorn and was used as meat substitute in foods. It is produced by continuous aerobic fermentation of food-grade carbohydrate substrates. And in hydroponics, there is a possibility of, in large-scale hydroponics, there's a possibility of using waste plant material to produce this kind of fungus. The main achievements of the project were the development and design of the Green Circle unit. The first Green Circle unit has been developed, designed and installed in our station in Fellsmúli, South Iceland. In our setup, we used Arctic char and Nile tilapia. The Green Circle is based on reutilization of water between two fish species, a cold water species, in this case Arctic char, and warm water species, Nile tilapia. Cold water from the Arctic char tanks flows into the tilapia tanks and is mixed with warm geothermal water. Warm water species such as tilapia can utilize feed residues and oxygen in the effluent water from the Arctic char. The warm, nutrient-rich effluent water from the tilapia tanks can then be used to cultivate algae. This flow-through system is the only one being used in Iceland. In our pilot station, in our pilot aquaponics unit, the recirculation of the water is 70%. Using this setup, it is possible to increase production while preserving and reusing water and heat. The design will be used as a model for future aquaculture stations that Matorka plans to build. The abundance of fresh water and geothermal water in Iceland creates exceptional opportunities for food producers, especially for poly-aquaculture and implementation of aquaponics or alga culture on fish farms. The Green Circle was developed to increase sustainable production of high-quality food for export by utilizing abundant resources in Iceland, especially geothermal resources, other renewable energy resources, land space, and clean water. We will continue developing new sustainable techniques, as well as perfecting the current system. Access to a steady supply of geothermal water is the cornerstone of the Green Circle system, without which it would be far from being feasible. Thank you.